Hello everyone, let us solve a very interesting question, and this question is from the real analysis part and asked in the 2025 TIFR PhD mathematics. What is given? Here f is a mapping from the real number set to the real number set and it is a continuous function. Additionally, this continuous function satisfies this equality. Okay. And in the question what is asking whether this function can be a non-constant function which lie in this space L2R, and in the second option it is saying that at most one function lies which satisfies this property lie in this L2R, means there cannot be more than one function in the Hilbert space L2 which satisfy this type of two property. And in the option C it is telling that these spaces of the function which satisfy this type of property is a one dimensional vector space, and in the option D it is saying that it is an infinite dimensional vector space, means that there are infinite numbers of linearly independent continuous functions satisfying this type of property. So we have, let us check which options are true. Okay, given what is given, for r greater than 0 f of x0 is equal to, this equality is given for every x0 belongs to r, for every any x0 this satisfies this type of equality for any r greater than 0. Okay, so we are dividing by 2 on the both side, it gives 1 by 2 r this quantity. One can ask why we are dividing this quantity, because we are converting it into an average sense. One can also ask why dividing by 2r is giving average, because we are integrating from x0 minus r to x0 plus r, and then we are dividing its measure. Measure means the length. The length of x0 minus r to x0 plus r interval is nothing but 2r. So when we divide its measure, so it gives the average value. Okay, means it is a very nice property of the Lebesgue theory that this average goes to f of x0, converges to f of x0, means the limit of this function is equal to this function, and those points x0 which satisfies this type of limit equality is called the Lebesgue point. Here we will use that concept. For the time being, believe me that this limit converges to f of x0 is equal to f of x0. For the time being, later I will provide the complete proof how this is coming, how this limit is equal to f of x0. Okay, how this average value is equal to f of x0, I will prove it later. For the time being, believe me that this value is equal to this. Then what it will gives? Then it gives nothing but f of x0 is equal to 0. But our x0 is an arbitrary point, means for all x0 it is giving 0. Therefore f is nothing but the 0 function, identically 0 function. So we are getting only one continuous function which is the 0 function which satisfies this type of property. So let us verify the options. It is saying that f is a non-constant function, so it is not true, because f is only function 0 function which is a constant. There exists at most one function in L2R satisfying this property. It is true, because the 0 function is the only one. The spaces of functions satisfying this is a one dimensional vector space. One dimension means it has infinite number of functions, but we are getting only one function. It is also false. And the last one is it is saying that it has infinite. It is this type of function spaces are infinite dimensional. It is not also true, because we are getting only the 0 function, so it is 0 space. Okay, so option D is also false. But our main task is to prove that this limit is equal to this, means every point is a Lebesgue point. This is the very nice property of the continuous function. Continuous, if f is continuous, then every point, previously I told that means this one, if x0 point satisfies this type of limit, then x0 is called a limit point. And I will prove here I will prove that for continuous function every point is a Lebesgue point, means every point x0 satisfies this type of equality. Here I forgot to mention that for all x0 belongs to R, and condition is that f is continuous, f should be continuous, then only I can show this one. For arbitrary functions, every point x0 may not be a Lebesgue point, okay, and at this type if is called the Lebesgue point. Lebesgue means Lebesgue, Lebesgue point. If a point satisfies this type of limit, then it is called a Lebesgue point, and for the continuous function every point is a Lebesgue point. I will prove this limit, okay. So what is given, let us proceed to prove this limit. Given that f is a continuous function, now I will consider this limit. I will show that this limit is converges to this, so I will consider the difference, this by using the usual definition of limit. I will consider this function minus the limit point. I will estimate it, okay, and this term are as it is kept, and this term can be written in this way. How? Because f of x0 is a constant quantity, and the integration of x0 minus r to x0 plus r, here it is, sorry, x0 plus r gives 2r, and 2r will cancel, so it is nothing but the f of x0. So this term can be rewritten in this way, okay. I hope up to this point everything is clear. Now I took merge these two terms because the limits are integral limits are same, and 1 by 2r is also common. I took 1 by 2r common, and r is a positive quantity, so it can also come out to the modulus, out of the modulus, so it can be rewritten this thing, okay. Then I will took the modulus inside, so there is a less than equality sign, and the modulus come inside this, okay. Now my final target is to pass the limit r tends to 0, because here we have to r tends to 0 plus. 0 plus is given because r greater than 0 is given, so we are coming from the right side, okay, only. Means I have to take the limit r tends to 0 plus. So since our limit is going r tends to 0 plus, so we can consider that our r lie in 0 to 1. So there is no harm to consider that r belongs to 0 to 1, okay. So this quantity, okay. Now I will take the supremum value of this quantity, and if I then it will be a constant quantity, and the integration value is x0 minus 2r to x0 plus r gives 2r, and 2r will cancel, so I will get this supremum value. Now I will claim that when r tends to 0, this supremum value is 0. How? If I can prove that if f is uniform, but f is given continuous, there is not a f is given continuous, but my r is less than 1, so this y belongs to what? Belongs to x0 minus 1 interval to x0 plus 1, because this interval x0 minus r to x0 plus r is a subset of this interval, means x0 minus r to x0 plus r, this closed interval is a subset of this interval x0 minus 1 to x0 plus 1, okay, this interval. Therefore I took r less than 1, okay, to make this inclusion, and means this interval is the subset of this interval, okay, and on this interval x0 minus 1 to x0 plus 1, it is a compact interval, and our function f is a continuous function, so there we know that every continuous function is uniformly continuous on compact interval, so therefore our f is uniformly continuous on this interval, okay. And this supremum value also can be written in this way, okay. And we know that from the property of the uniformly continuous, when r goes to 0, this supremum value also goes to 0. This comes from the uniform continuity, and uniform continuity on this interval, and this interval is a subset of this interval. Therefore we can apply the uniform continuity of our continuous function. So therefore this limit goes to 0, and this limit is this term is exactly equal to this term. Here it is written in the expansion form, it is written in the notation form. So when r goes to 0 plus, it goes to 0. So therefore when we will take limit on the both side in this term, so this term will goes to 0. So this limit is equal to 0, this one. Okay, so finally we established this thing that limit r tends to 0 plus 1 by 2r, this integral is equal to f of x0. So we proved our claim. I hope that you all understood it very well. Thank you. See you again very soon. Okay, bye bye.